Okay, wow. Thank you everyone for showing up. What an esoteric topic for Thursday. Hello, I'm Saveen Reddy from the Azure Data Lake team. And I'm going to talk today about some fun stuff with Azure Data Lake Analytics and U SQL. And as a bonus today, we have Dr. Michael Reese, inventor of U SQL, with us. And I got to say, honestly, he is the U SQL expert. I am just a dilettante in this field. Oh, he's going to give you the volume.
Okay, now it works. So he's a very good presenter, so he will talk everything about how to use U SQL in Data Lake.
Yeah. And Michael will correct me. Okay, I want to tell you what happened that made me want to do this session. And it actually happened 3 years ago on Hacker News. So someone posted the following thing, the New York Public Library, and he's like, they have 2 million images. These are like book covers, right? And they're, I think, like 25 to 35 megabytes each. They're TIFF files, they're uncompressed. And he just wants to make thumbnails. That's the entire thing. I think this was going on the New York Public Library website. And you know, he calculated that, you guys are familiar with image magic, this would take 115 machine days, okay? And that's kind of challenging. Now, some things about this that struck my chord, because at that time, I was already a couple of years into the Cosmos team, Microsoft's internal data lake, was that this seemed like a very bursty activity. Like he was only going to do this one time, it wasn't a regular process. Number two, this is stupidly parallel. Clearly, if we could just convert all a million nodes, we would just do that, right? Subject to money constraints. And the other thing is like, wow, we used Data Lake and Cosmos so much, and our language, U SQL, is so expressive. This, I claim, if you think about the time you spend as a developer, it would be easy to get this done in the system. And you know, I'm not going to lie, there are some rough spots, but I think you'll see it, I'll show you. We're not going to spend a lot of time on it. Okay, so let's just talk. Okay, these are our promises for Azure Data Lake. Start and second, scale instantly, pay per job. What that means is on every query, you get to say how many analytic units or nodes you have allocated. And that's actually the secret to this, is that slider, how many nodes per query, and we're going to develop a massively parallel program, and we're going to see a little bit about how you optimize these things. So, traditional, if you're doing sort of big data, if you're doing traditional SQL, it's declarative, but extensibility is hard. If you're doing traditional programming, it's very extensible, that is like C# or Java, but it's really hard to scale, right? U SQL gives you the best of both worlds, right? Now, oops. I just want to do a few notes. Number one, I'm not focused on like data lake store ingress and egress upload speed. That's kind of a different topic. We'll talk a little bit about what you would do for imaging library choices. And again, I want you to keep in mind how fast, not how fast the code runs, which is pretty fast by the way, but how fast it takes someone to actually get the solution going, right? And just how many few concepts there are to really think about. And we'll talk about organizing data and dollar signs, cost. Okay, and again, we will not be discussing egress. How do you get things from the cloud down to your machine? That's another topic. Okay, furthermore, focused on batch processing, not streaming. I think once we get streaming online in our service, this will be an interesting demo next year. Another thing is, when you do big data, you know, Michael and I are familiar with data that goes from gigabytes to 5 petabytes. And the solution that works at a terabyte is not the solution for a petabyte. So one answer will not, you know, scale indefinitely. Different patterns are there. And of course, your mileage will vary depending on your specific problems. So just to compare what the Hacker News developer wanted to do and what I'm talking about, he had 2 million images. I have 1 million, and we have done 100 million, and we could do any arbitrary number, as a matter of fact. His images were big. My images are much smaller, from 1 megabyte to 4 megabyte. That wasn't intentional. Right now, U SQL has a limit of how much can fit in a row, which is about 4 megabytes. This is something we're working on. So internally, our internal data lake does a 250 megabyte row. So we're going to figure out some options there. His was TIFF, mine are JPEGs. He didn't say what format he wanted. I'm picking JPEGs. And he's doing scaling, and I'm going to do scaling, and maybe we'll talk a little about how do you integrate cognitive into this scenario. Okay, so let's just look at how you would do this sort of on the command line. This is the imperative way. You read a bunch of JPEGs, and one by one you do a resize. Pretty obvious how this works. This code's available on TechNet. Now, that's the traditional approach. If you had to scale that out to 1 million images, or 100 million, you'd have to scale your code. That means you have to think about distributing the code to different machines, error handling. The problem gets rapidly complex. USQL, the way I would talk about it, I'm really curious, Michael, if you're going to say anything, is you actually scale your data. That is, how you partition your data is what determines how you scale, not how you write your USQL queries, right? It's a very different philosophy. Okay, so what kind of, just to back up, what kind of imaging we want to use? We need resizing, obviously, it should be fast, good quality. Needs to run on .NET 4.5 because USQL itself runs on .NET 4.5. In the future, we'll consider other .NET versions, like .NET Core. There are memory restrictions. So each vertex in a USQL query has about 6 gigabytes that it shares with the operating system, the USQL runtime, and the vertex code. And finally, each UDO instance has a limit of 500 meg. So those are the constraints we have. In the future, we're working on giving you sliders to change the constraints. Michael, is there anything you want to add about the constraints?
No, I think that's approximately right. One thing that is, you already mentioned is that while you have to have your image fit into a row if you want to put it into a row, you can process bigger blobs inside your custom code as long as the row that you're generating is smaller than 4 megabytes.
Right, right. One more thing, I would really like if the solution was built into Windows. I don't want to give more code. And my preference would be pure .NET. I don't know if that's really possible. But I did probably the cheapest thing I could. I picked GDI Plus, which I've written extensively. This is not what you should do, but it's the simplest solution. What I really should have done was pick Direct2D, right? It's built for server-side imaging. You can see this link, which goes to great explanations. And by the way, I'd really highly recommend you read this article if you're interested in the topic. So this was published very recently, and for .NET Core image processing, this guy has laid out, he actually talked about scaling specifically, and he gave several options in terms of performance and image quality. Please read the article, and I probably, if it wasn't going to be Direct2D, I would have picked probably this one, right? The rest are wrappers or maybe image sharp. Okay, so here's the general pattern in this batch scenario. We're going to upload, I'm not going to talk about that. We're going to prepare the data and organize it into a table. We're going to do the processing, of course, and then we'll create the outputs. And then the final step I'm not going to talk about is download, of course. That's egress. So we have a lot of images, and I put them into a table. I'm going to show you how I did it, and we'll talk about why it's done this way. You can notice I actually have one huge TSV file. It's about 59 gigs, which contains 1 million images. And I'm just reading it, I'm just putting it into a table, which is called Megaface for this demo. Now, oops, there's a slightly different problem here. Oops, slide went out of whack. Sorry. I'm missing a piece of code in another sample here. I could have extracted multiple JPEGs in a folder, right? And then done the same thing. Why did I choose this mechanism? The simple reason is that today in USQL, file set resolution, that is reading one file over another, takes a fixed amount of time per file. So it wasn't good for me because it times out in about 5,000 files. The good news, Michael has, they've introduced a faster version of this. So you can do, what's the limit now, Michael?
Right now the goal is to get to at least 100K.
100K. So it'd be something like select image file name, image data from, star.jpg, where the number of JPEGs in the folder are 100,000 files, and eventually 1 million, and you'll directly be able to insert in the table, okay? One more thing about the table, you notice I've clustered by the file name and distributed by the file name. I want an even partitioning, that's why I chose hash distribution. Okay, now that's 1 million images. I chose, again, this pattern because if I have a bunch of file names, and we don't support 1 million right now, I have to do it in multiple scripts. So I kind of cheated, but I think it's a reasonable cheat for this demo. So here's the baseline. This is about the smallest piece of code, and everything should be this size or larger in terms of execution. This is, and we'll talk about what's happening at the top. I have some C# code that's been uploaded into the server. Let me just show you the code for a second. So in the U SQL catalog, in the, oops, I'm in the wrong one. 1 second. This is it. In the build database, under the assemblies, I have uploaded demo.asm, which is just a single CLR, a .NET assembly. I'll show you the code. It's exactly this. It's the simplest piece of code you could ever imagine, right? Demo namespace, a single static class, and just a create thumbnail, which takes bytes in and bytes out. This is normal GDI stuff. There's nothing special about this code. It'll run on your local machine, it'll run on the server, and this is a normal C# project. And all I did was I right-clicked on the C# project and said, register assembly, and I'll just show you what happens when I do that. I'll pick which account I want to upload it to. Let's just pick a random one for a second. And then it'll pick which database I want to upload it to, and I'll give it a name, and this one would have been called Demo ASM. And I loaded a master here, and I hit submit. This means that now this code will be available to all U SQL scripts, okay? Now what does the code look like? I showed it to you in the slide, and let me just do one thing here. Comment this out for a second. We'll explain this a bit. I load the code here with reference assembly, so now my U SQL code has access to that. I select star from the million images in that database, okay? And then I'm just going to select file name and call a helper method. And I showed you the code for the helper method. All it does is normal GDI code to create thumbnails. And then I'm going to place this in another table as opposed to files. And I'll explain why in just a few minutes. If the table exists, I will delete it. Otherwise, just insert the images in the table, okay? So when I run this, this will take about 2.5 minutes. And let me I have the numbers with me. Oops, sorry. So here's the code. If this is doing nothing, this will take about 2.5 minutes. And now notice, if I assign it 100 AUs, 100 nodes, it's 2.5 minutes. If I assign it 20 AUs, it's still 2.5 minutes. That is to say, I've been driving the slider up and down. Let me show you the slider just so everyone's clear on what I'm talking about. When I submit this script, now my account is special. I can assign 1,000 nodes to this query, or 1. So I asked for 100, and so I asked for 100 here, and then I dialed it down. And here's what happened when I asked for 100. The performance analysis tools actually told me something quite interesting. It said, you asked me for this. These are how many active nodes I actually have, okay? And so what's really funny is, it actually, I clicked on this button called AU Usage Modeler, and I can actually see it right here. Obviously, I shouldn't ask for more than 20, and we'll talk about why it picked 20, okay? Now I did with 20, and this is exactly what happened. By the way, it's much better usage, obviously, right? The graph is a bit scaled. So, any guesses on why it actually did not use 1,000 nodes? Say it again? Okay, so let's upgrade it. So essentially, that's the U SQL optimizer. It's related to throughput. Here's what's happening. The U SQL optimizer is breaking up the job into small pieces of work, okay? And these are the vertices and the stages. Roughly speaking, it's trying to pick a sweet spot of several gigabytes per vertex. It's, I believe, 4 gigabytes, right? Between 1 to 4. So what it's saying is it believes there's no point for me to use all 1,000 or 100. That's why it only allocated 20 and the rest is wasted, okay? And we'll talk about how you can force the behavior in a second. Michael.
Aware that you will be paying for the wasted resources.
That's right.
So
That's
we
right.
will be happy, but your
you may not be
accounting
happy.
team might not be.
Okay. Okay. Now here's the simplest thumbnail thing, which does nothing, okay? But what it does is, I'm going to prove to you I'm calling C# code, and I did 1 million images, and guess what? The execution time didn't even change, right? So just calling C# code didn't cause a problem. Let's do something. Okay, now I'm going to call the actual create thumbnail, right? The code I showed you before. Let's see what happens. And actually, this is slightly off. It took about 3.8 minutes to do this, right? Because there is actually real work now happening in GDI+. Okay, so 1 million images got processed in about 4 minutes. And I could have dialed this down to exactly 20 nodes. So in short, I didn't spend a lot of money to accomplish this scenario. In fact, just in case you're wondering, how far did this go? We have done 100 million images with 2,000 nodes, and I believe that took about 45 minutes. Just think about that, right? 100 million images in just 45 minutes, and you just paid about $2,000 for that, right? And we can actually make that cheaper over time, by the way. What's that? It's a big improvement, right? Yeah, it's a huge improvement. And what else is the improvement is, did any of the code I write, did it seem complex? Right, it really didn't, right? It was just, I'm mapping some data in, I'm processing with a simple C# function, and I get my output. Now there are a few little complexities. Now, I have it in a table. How do I get the files out? Michael.
Well, right now you would have to write an output statement for each select with a filter predicate to identify the one row that you want to output into the image.
So so the problem is today we don't have the ability to get output rows from a key in the data. Now, fortunately, and Michael, I may have the syntax wrong here, but I think it's very close to this. It's very close to this. What I'll be able to say is I have 1 million images here that have file name and image data. Use the file name as the file name. So this will output 1 million images, right? And again, look how trivial this is. I didn't have to think a lot to make this happen, right?
So just as a caveat, so this is a feature that will come this summer.
This summer.
And we are still working on the scale. So 1 million, 100K, we'll have to see.
Yeah, but we want big scale, Michael.
Yes.
We need a... Okay.
Caveat from the engineering side here.
Here's where we get a bit crazy. I was given 1,000 nodes to run for build, which, by the way, is a lot of capacity in our service, right? And you notice the system only let me use, well, it only could use 20, okay? What if I was crazy enough to say, I'm going to force you to use all 1,000, okay? And there's two ways of doing it. This is the processing way, and I also have the way I would do it in my script today, right? And what I'm telling it is, look, ignore the optimizer. Don't try to put 1 to 4 gigabytes to each vertex. Go ahead and try to assign it out, partition it by the file names, which are of course unique, to each vertex, and use all 1,000, okay? So, what actually happened? Let's see, I have this job, I just ran it. Now the good news is, this job is using, 50 times more than I originally asked, or 500 times actually. It still ran in 3.3 minutes. Notice it's slightly longer. Okay, we'll think about why that's the case. You can sort of see here, I will zoom in for you. This work was actually distributed in this stage to 1,000 vertices. So all the vertices are actually being used. Now, having said that, this is all charming, and it only took 3 minutes, so I was paying for 1,000 nodes for 3.3 minutes. This is probably a pretty silly thing to do on my part, because each node is spending a small amount of time and a small amount of data. The throughput is not great per node. Let's take a look at why. That was an aggregate phase. It's called SV aggregate, and you see all these nodes, 685, 689. These are the 1 to 1,000. Notice we have each node handling just 28 megabytes of data. right? So we're just we're really stupidly partitioning. If the nodes are doing heavy amounts of work, like each one spending a minute per image, this makes a lot of sense, because you're really expanding out what the work is. But I kind of wasted the time here. I just wanted to show you how easy, though, it was to actually scale out from 100 nodes to 1,000 just by forcing it. Michael, you need a...
Well, one thing that you also might want to see is there's like a really big blue area there, and then there is a smaller green area.
Yeah.
The blue area is basically every time you spin up a node, you have to image the node's code that gets executed. And if you have custom code, that has to be done on every single vertex. And and that takes like, I don't know, a second or so.
Yeah.
And now if you're now only running for like a very short amount of time on that node, then that blue part will start to basically dominate your like cost. So the goal there is to pack more data into a node so that it can like do more processing to get the blue part like to be only a small fraction.
So as evidence, take a look at the runtimes of these vertices. It's 5 seconds per vertex. It took more time to set up the vertex and copy the data to it than to run it. So this was a little silly. If the vertex have been doing a lot of work, then this makes a lot of sense. Okay, now to sort of wrap it up. I have a bunch of references. The deck is going to be made available. Some things to think about for the future. I think we've really got to make this in million files things a bit easier to deal with. Number 2, use direct 2D and system net drawing. And again, I could only handle like up to 4 megabyte images, and we're working on relaxing the limitations, so you can do like, like 200 megabytes, that kind of thing.
Mm-hmm. Now in this case, actually, one recommendation I would give is instead of doing the resizing of your image in the context of a processor, you could theoretically do it inside an extractor if you're operating on the files directly. At that point in time, the files can be bigger than 4 megabytes, just the thumbnail has to be less than 4 megabytes.
So I want to thank everyone for your time. I think this shows you how simple it is to actually do something very scaled out, right? Okay. Thanks, everybody.